Okay, college algebra or intermediate algebra students, thanks for watching this video, and thanks for being flexible with me as I attempt to manage our engineering transfer program. But so here we go. All right, the first question came from Chris, who sent it to me very quickly while we were still in class, actually for the afternoon class, and that one came from this one. And there's a little bit of good news for you guys here. It's x plus 3, x minus 4 is greater than or equal to 0. The sad fact of the matter is that we don't really have the tools to do that. Now, Alex included it. I'm not a fan of it because I just don't think we know how to do it. So this is from Chris D. This is something like x plus 3 over x minus 4 is greater than or equal to 0. We really don't know how to do this. And, there's this kind of stupid way, and Dean showed it in class, but it's kind of a magic trick. You don't really understand how to do it. So Chris, thanks for submitting your request, but I actually eliminated this from the pi. So we won't cover this. All right. So no worries there. All right. Number 2. The next one we had was from Elisa. And she gave me one that looked something like this. It was similar to simplify. Let's see, square root. No, I think it was the 5th root of something like 96 a to the 11th b to the 10th c cubed, something like that, right? And so what do we do with this? Well, the first thing we can do is recognize that this thing really means I can write this as 96 a to the 11th, b to the 10th, c cubed, all to the 1/5 power. Right? And so what do I do with that? I split this up into several parts. All right. Now, some of you may know that there's a better, more efficient way to do it, but I'm going to do it the long way. I'm going to write it as 96 to the 1/5, and then a to the 11th to the 1/5, and b to the 10th to the 1/5, and finally c cubed to the 1/5. All right. Well, what can we do here? The only real good news we've got is that this is going to be pretty convenient here. Right, so what do we do there? We multiply, right? A power to a power, we multiply the exponents. So the only really thing that works well with this part is this will become b squared. All right, b to the 2nd, but that should be a 2. Let me make that a little bit more like a 2. b squared. All right. This not very convenient, this not very convenient, but what I'm going to do with this one is write this as a to the 10th b a to the 10th times a to the 1st, all to the 1/5 power. Right? Why do I do that? Because then it becomes this becomes an a squared, and this becomes just a to the 1/5. All right. And so that leaves this thing is just c cubed to the 1/5 power. And that's that. Now, the one thing I've been kind of avoiding is this guy here, right? 96 to the 1/5. What am I going to do with that? So let's put a big orange question mark by here. And I'm going to run over here and do a quick side note. So let's investigate some perfect fifth powers. Okay, well, 1 to the fifth equals 1 times 1 times 1 times 1 times 1, which equals, surprise, surprise, 1. All right, well, that's not terribly useful. 2 to the fifth equals 2 times 2 times 2 times 2 times 2. And that equals, let's see, 2 times 2 is 4, times 2 is 8, times 2 is 16, that equals 32. 3 to the fifth equals, let's see, 3 times 3 times 3 times 3 times 3. How am I going to do this? Well, let's look at, this is 9. That's 9, and that's 3, so 9 times 9 times 3 is 81, so 243. So even just knowing these few perfect fifths here, you know, I look at this 96, I'm like, well, I certainly can't fit a 243 into there, but I can fit 32 goes in pretty nicely, so I'm going to write that one as 3 times, 32 to the 1/5 power. Right? Why do I write it like that? Because then I can change this to 3 to the 1/5 times 32 to the 1/5. Right? Well, I know 32 to the 1/5, this is 3 to the 1/5 times 2 to the 5th to the 1/5. So this really equals 3 to the 1/5, or the 5th root of 3 times, well, this just becomes 2. And then all this stuff comes down here. A squared, a to the 1/5, b squared, and, well, that doesn't really do much good, so I'm going to write that as the 5th root of c cubed. Alright, so it's kind of a mess right now, but I can see that some of my stuff worked out nicely. You know, I split the 96 up into a 32 and a 3. I split the 8 to the 11th up into a 10 and a 1. Why a 10? Because the 10 is a power of 5, or a multiple of 5, and 8 to the first is just what I have left over. The b to the 10th worked out nicely because that's just, you know, that's also a nice multiple of 5. And c cubed, well, there's nothing I could do with that, so that just stays c cubed to the 1/5, which is still the 5th root of c cubed. Alright, and so I'm going to do this again on the next page, and we'll split it up a little bit faster, and we'll see the faster way to do this, and then we'll clean it up. So 96, 8 to the 11th, b to the 10th, c cubed. So this is Elisa continued. Alright, so it's the 5th root of 96, 8 to the 11th, b to the 10th, c cubed. Okay. What I'm going to do is split this up into all my nice perfect fifths right away. So I'm going to say it's the 5th root of 32 times 3, a to the 10th times a, b to the 10th, which is nice, And the c cubed, nothing I can do with that. It's too small to take a fifth root. And so I know that this becomes the fifth root of 32 is 2 times the fifth root of 3 times a squared times the fifth root of a times b squared, and then the fifth root of c cubed. Now all the fifth roots that remain, kind of all my leftovers that didn't work nicely, will kind of stay under the radical. And what do I have left outside? I've got a 2, I've got an a squared, a b squared, and then I'm going to be left with the fifth root of, what's left here, a 3, a, c cubed. Okay, so let's make a little map of what we did there. The 2 is from there, the a squared is there, the b squared came from there, and then the cubed root, the stuff that I've left over, the 3 came from there, the a came from there, and then the c cubed came from there. All the stuff that worked nicely, the 32 became the 2, the 3 was there, the a to the 10th became the a squared, the b to the 10th became the b squared, and the c cubed, nothing happened there. Okay, so that's, in a nutshell, how to do Elises problem. Now, there are actually very few people emailed me questions, so I don't really have that many problems left to do. So let's take a look. Cass said that numbers 18 and 20. 18, 20, and 8. So let's write over here. Cass said homeworks, what are they, 8, 18, and 20. Okay, so let's look at those. Now, I don't have the exact same homework here, but I've got one similar. So let's look at number 8. All right, the fourth root of 16 over 625. The fourth root of 16 over 625. Let's simplify that. The fourth root of 16 over 625. So number 8 is the fourth root of 16 over 625. Well, I can break this up into the fourth root. Similarly as we did it with exponents, I'm going to write this as 16 over 625 to the 1/4 power. And so that will equal 16 to the 1/4 over 625 to the 1/4. Okay, so how do we deal with that? Well, you might guess, and you would guess correctly, that this is some power of 2. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So this just works out to be 2 to the 4th to the 1/4. And this actually works out to be 5 to the 4th to the 1/4. Right? So those neatly cancel out. So this just works out to be 2 over 5th. All right? Or 2/5, and that's my final answer there. So that was a pretty good one. Thank you, Cass. Let's take a look at number 18 here. I've got to go back to that homework. What is 18 all about? Root 63 over root 7. That's a good one. So root 63 over root 7. Let's do that. So number 18, homework number 18 is square root of 63 over the square root of 7, and we're supposed to simplify that. Well, again, this is a square root. It's the 1/2 power. So we're trying to think, are there any nice, clean, perfect squares that go into 63? Sure there are. I can write this as the square root of 9 times 7 over the square root of 7. Now maybe already you can see how this works out. It's going to be the square root of 9 times the square root of 7 over the square root of 7. Now, as you might imagine, I've got an all-powerful red pen of cancellation. These cancel out, so this just works out to be square root of 9, which equals 3. Okay, easy enough. They boil down very nicely. And then the last one to do is oh, that's the wrong page. Number 20. Okay, now here we have to multiply. 3 plus 2 root 5, 3 root 10 minus 4. I might have to go back and forth a couple times. 3 plus 2 root 5. So homework number 20. 3 plus, and oftentimes we read this as 2 root 5, or 2 times the square root of 5. It's just faster to say 2 root 5. And then the other one is 3 root 10 minus 4. 3 root 10 minus 4. Okay, well, what do we do with this? If we kind of break this down a little bit, we see that it's just something plus something else times something minus something else. All right, that certainly looks like FOIL to me. So we're just going to do this old front, outside, inside, last, or first, outer, inner, last, or whatever you want to call that. So it's going to be this multiplied by this, and this multiplied by this, and then down here we'll have this multiplied by this, and this multiplied by this. All right, so how does that work out? 3 times 3 root 10, so it's 3 times 3 times root 10. That's my first. And then my next one, the outside, is going to be 3 minus 3 times 4. The next one is going to be plus 2 times 3, or 2 times root 5, times 3 times root 10. And then the last one is going to be minus 2 root 5 times 4. All right. Now let's do a little housekeeping here, or maybe we should label our FOIL. This is front. This is out. This is inner. And this is last. Okay. Is there any cleaning up we can do here? Sure there is. Well, 3 times 3 is 9. So this just becomes 9 root 10. And then 3 times 4 is minus 12. And this is, let's see, 2 times 3 is 6. I can multiply these in any order I want to. And remember, I can treat these just like an exponent. Root 5 and root 10 is root 50, and then minus 8 root 5. And for that one, that's all we can do. Alright, so because we've got a root 10, a root 50, and a root 5, 12, there's no like terms to work with here. There's no like terms to combine. Right, so not much we can do with that. Okay, well, that was it. We didn't do many problems. Let's go through and count them. We did 1, 2, 3, 4, 5, well, I guess kind of 5.5. We won't count this as a problem because I just told you that we don't have to do it. So 5 or 6 problems. It's not the 7 or 8 problems that I was hoping to do, but that's all the requests I got. So thank you for those who sent a request. Bonus points for you guys. And for those who are watching this on Wednesday, enjoy the day off math class, but I hope this is fun watching this in your PJs. Alright, take care, guys.